This lecture is about neural nets, which are one important tool in artificial intelligence over the past several decades. They were inspired by the brain, but even now we're missing all sorts of detailed information about how the brain works, so it's just an inspiration. One of the important features of neural nets is that they just involve numerical processing of the sort that simple cells might be able to do. They don't involve complicated sets of instructions, just simple numbers. However, even so, they can do some really complicated things when you put them together in a big network, like the brain. But the intermediate steps in a neural net are very hard to understand or interpret. They're a system that's not hard to comprehend in the abstract, but it is very hard to get a concrete understanding of what is going on in any particular neuron in any particular net. We just see that it works. So let's begin. So what is a neuron? If you look in a biology textbook, you'll see a diagram something like this, where there's lots of parts and lots of connections. However, we're not going to worry about all of that. All that matters for us is that it's a kind of cell that has some parts that receive signals or inputs from others, and some part that sends signals or outputs to others. These signals are something like electrical currents that can have different strengths. In this diagram, I've only got three neurons. However, in the actual brain, there are tens of billions of neurons, each of which is connected to thousands of others. Now, we're not going to worry about any of that level of detail when we're talking about neural networks in a computer. In the diagrams that we're going to use, we'll just represent each neuron by a circle. And there's going to be arrows indicating when one neuron sends a signal to another neuron. And the specific thing we're going to do is we're going to say each neuron is going to have some activation, which is a number. In this case, I'm using numbers between 0 and 1, but it could theoretically be any sort of number. And what a neuron does is it takes the numbers that are coming from the input neurons and it adds them up and then does some simple calculation to send its output. Now, the simplest possible thing would be for the neuron to just add them up and then pass that number as its number to the next level. But it turns out that's not going to quite do anything particularly interesting. However, some other simple functions can let us do something interesting. The simplest one, which we call the step function, just checks, is this sum, in this case 1.88, that's the sum of the inputs, is that above a threshold or below? If it's above the threshold, it sends a 1, it fires. If it's below the threshold, it sends a 0, it doesn't fire. Now, there are slightly more complicated things that a neuron can do. This is already enough for some neural nets, but there are more complicated ones that do some more interesting things. Two others that I'll mention are the sigmoid or the ReLU function. The sigmoid has its name because it's shaped a bit like a stretched out letter S, which is an unusual version of the Greek sigma. ReLU stands for rectified linear unit. I'm not going to say what that means. I'm just giving you these names in case you want to learn more. Uh, but what happens in each case is that we just add up the inputs, figure out where that number 1.88 is on the x-axis, see what value on the y-axis corresponds to that, and then the neuron sends that number as its signal to the next neurons. I won't say much about why people prefer different ones of these functions for different kinds of neural nets, but they all have the same feature, which is that as the sum of the inputs gets bigger, the output it gives eventually gets bigger also. The step function has a very sharp discontinuity there. The sigmoid function does it in a smooth way, and the ReLU function has some other features that are relevant for calculating some of the things that go on, but I won't mention any of the details. Each of these functions is just called the activation function of the neuron. And it says, how does the level of activation of the neuron depend on its inputs? I mentioned that with the step function, we're checking whether the sum of the inputs is above or below some threshold. The little graph I've drawn here puts that threshold as 0, but if we put it at a different point, we can say that there's a bias to the neuron. If it's a positive threshold, then the neuron is biased towards not firing unless it gets a lot of input. While if you give a negative number as the threshold, then it's actually biased in favor of firing unless it gets a lot of inputs that are negative. Now here, I'm going to add two more features to this chart. The green 1.0s there indicate that initially each input was counted fully and equally to produce the value. The red 0 here indicates the bias of the neuron. We said that each input was just added up to produce the value that goes into the activation function. The bias is that red number, and if the neuron is biased against activation, maybe it has a negative 1.13, and then in that case, instead of adding up to 1.88, it only adds up to 0.75. Now, we had also assumed that each input got counted fully and equally, but maybe sometimes some of them will be counted extra, some will be counted a bit less, and some might even be counted negatively. So in this case, the first neuron is getting counted with a 1.23. The second one is being counted a bit less than fully at 0.71, and the last one is being counted negatively. Each of these numbers gets multiplied by the activation of that input neuron, added to the bias, and then we get the result that goes into the activation function. And these green numbers are called the weights. The red number is called the bias. There's always a weight for any arrow connecting one neuron to another, and there's a bias for each neuron. Okay, so early neural networks consisted of three layers. There was one layer of neurons that just got an input directly. These had certain weights that they were each sent to the hidden layer. Each of the neurons in the hidden layer had some bias, took in its inputs, multiplied by their weights, fed this into an activation function, and then activated. And then the neurons in this hidden layer were each connected to neurons in the output layer. And those output layers also had their own weights and biases and activation function to determine the final result. Uh, Now note with this one, even though there's only 3 input neurons, 4 hidden neurons, and 2 output neurons, there's already 20 weights and 6 biases. We could imagine setting these weights and biases intentionally to do something specific, or randomly, or by tuning them in some other way. If we set them randomly, the neural net's obviously not going to do anything particularly interesting, but it turns out setting them randomly and then figuring out a way to tune them to get to the right values is the way that most modern neural nets work. So let's see an example where someone might intentionally set the weights and biases by hand. So here's an example. We could imagine that a professor has made a pass-fail test where you need to get a score of 60% in order to pass, and there's 4 questions, one of them worth 20%, one of them worth 25%, one worth 30%, and one worth 25%. We can represent the grading of this test by a very simple neural net with 4 weights, one for each of the input questions, one bias to determine what threshold you need to pass or fail, and step function activation to say you either pass with a 1 or you fail with a 0. And now we would enter the score on each individual question in the input neurons. These would get multiplied by the weights. And if the sum of these values is greater than 0.6, then the output is pass, and otherwise it's fail. It could be that the score on each question is either a 0 or a 1 based on whether you got it wrong or right. Or we could imagine that the professor has some more complicated system for giving partial credit, but still needs an overall score of 60% in order to pass. Of course, in this example, this is very simple. No one would build a neural net to do this, but this is an illustration of just what a very simple neural net looks like. Now we could imagine this feeding into a more complex example. So imagine that the professor has 2 tests over the course of the term, and test 1 has the weights and biases that we mentioned earlier and its step function activation. Maybe test 2 has a different set of weights and biases for its questions. And then the output from each of those 2 tests each gets a certain weight and gets fed into the activation function for the grade in the class. In this case, you need to get at least a score of 40%, that's the bias there, in order to pass. That is, we're representing the output of the class as a ReLU here, you get a 0 in the class if you don't get at least 40%. But if you get more than 40%, then your score goes up sort of linearly based on how much you got above that. Again, no one would probably actually build a neural net like this to score students in a class, but it illustrates how this sort of thing could be done by hand and how, in order to set a neural net by hand, you'd have to have some understanding of what each particular neuron means and what each particular weight means and each particular bias means. Now, there are more interesting examples that you can do with neural nets where you try to learn something from some data. So let's imagine that we have information about a whole bunch of different houses, maybe the square footage of each house and the distance each house is from the beach and the price of each house. On the right, what I've done is I've graphed all the different points corresponding to these different houses. And then we could imagine maybe there's a neural net that is trying to guess the price of a new house on the basis of its distance from the beach and its square footage. The weight of each of those two factors is going to show how much does the price depend on that factor. And the bias is going to show what's the basic price for a house that is 0 square feet and 0 distance from the beach. In this case, what we've done is we've found what is the best setting of weights and biases that allows us to most closely match the data. And I haven't said exactly how you find that. There's all sorts of mathematical techniques that statisticians use, but you could also imagine what's going on is that someone just has a knob for the weight 1 on the distance from the beach and a knob for the weight 2 on the square footage and another knob for the bias. And we could imagine if you wiggle all three of those knobs, then that red plane is going to change its angle, move up or down. And you could start with it in some random orientation and just tune all three of those knobs until it matches the data fairly well. And this is actually how the very first neural nets were trained. They literally had knobs on a device with this sort of continuous activation. This was back in the days of vacuum tubes, even before the transistor was invented. But now that we have this basic idea that each of these weights and biases means something about how the input gets translated into the output, and we can just try wiggling each of them until we get a function that does a good job of matching the data, we can start talking about more involved examples. So here's an example of how we might set up a neural net as a spam filter for email. Each of the input neurons here corresponds to some word, and it's just going to count how many times does that word appear in the email message. And then we could imagine putting weights on each of those, feeding them into a single neuron. In this case, I've given a neuron with a sigmoid activation, have some bias on that, and it'll take all those weights and biases and determine, is this spam or not? If there's a high number, it's probably spam. If there's a low number, it's probably not spam. Now, if we just have a single layer structure like this, where these inputs counting how many times each word appears just go directly into the output, then it's not going to work very well. The only thing we can do with a single layer structure like this is just some words have positive weights, meaning that if they occur, we think it's more likely to be spam. Some words have negative weights. If they're in the email, it's probably not spam. And a lot of words are probably going to have a weight that's close to 0, where they could occur either in spam emails or not spam emails. But this sort of structure is going to make it impossible for words to interact. If you're someone who studies Africa, you might get emails from your professor that talk about Nigeria. And you might also have a bank account and get emails from your bank that talk about funds. And you might think those emails should not be marked as spam. So neither the word Nigeria is a spam word nor the word fund. But if there's a single email that talks about both Nigeria and funds, that might be more likely to be spam. Now, we could try to do this with some sort of slightly more sophisticated model. If we create an extra layer of neurons here, we could imagine each of these neurons will try to recognize a certain category of email. Maybe one of these neurons will try to recognize school emails. It'll find all the words that are associated with school. Another neuron will try to recognize family emails, all the words that come in emails from your family. Maybe another one tries to recognize which words appear in Nigerian print spams and find those. And then once we've got a weight for each of those kinds of email, we then take those weights together to figure out is this spam or not. But once we realize that each one of these neurons here in the middle might represent some feature of an email that's determined by its words, we don't have to think of them as full categories. We can think of these features as themselves interacting that then maybe determine some other higher level feature that then determines some higher level feature. And then it's only after several layers that we get to the determination of whether it's spam or not. And so this is the inspiration behind the idea of what they call a deep neural net. It's called a deep neural net just because it has more than 3 layers. Uh, there's no specific number of layers that it has to be deep, except more than 3. But many modern neural nets have 10, 15, 20, 30, dozens of layers. Here I've illustrated one which has one input layer of 10 neurons, 3 hidden layers of 4 neurons each, and 1 output neuron. In this case, with just 10 input neurons, 4 in each of the hidden layers, and 1 output, we have 76 weights and 13 biases. 1 weight for each of those arrows, 1 bias for every neuron other than the input layer. Now, in a spam classifier, we're going to have all the words that could possibly appear in email and the input layer. And then we'll probably want to have several dozen neurons in each of the hidden layers. So if we just do that, we're going to have hundreds of thousands of weights and hundreds of biases. And the human brain has tens of billions of neurons, each connected to thousands of others, and each of those connections has some sort of weight. Each neuron has some sort of bias. So if we're going to build a neural net that big, we're not going to be able to do it by hand, either by directly programming in those weights and biases or by tweaking the knobs until it looks right. Instead, what we're going to do is we're just going to start with lots and lots of training data, the text of lots of emails, and a classification of whether it was in fact spam or not. Now, we'll do something that is very similar to what we did in the house example. We'll just wiggle each of these weights and biases to get it closer to a match. Now, we're not going to do it by hand. Instead, there are various mathematical techniques that we could do to figure out how tuning one of these weights or biases will get the overall result closer. I'm not going to go into the details of these techniques. In order to properly understand it, you'll need a bit of calculus and a bit of linear algebra, but just a bit of calculus and just a bit of linear algebra. You could probably get it from just one class in calculus and one class in linear algebra, and then just go watch any of the videos about these techniques for training neural nets. You don't need as much math as a lot of science degrees need. But the important thing is we will start with our neural net just randomly designed with random weights and random biases. And with that random starting point, what's going to happen is that each one of these neurons is going to represent a different random feature of the email. And then once we start tuning things, they'll start representing things that in some sense are more meaningful. However, there's not going to be any guarantee that they end up representing anything that we humans can interpret directly. All that's going to happen is that these weights and biases are somehow going to add up in such a way that the emails in our training data that were spam will be marked as high probability of spam. The emails in our training data that were marked as not spam will be marked by this neural net as low probability of spam. There's not going to be any specific meaning that is given to us by any one of these neurons in it. And there's no simple logic we can do. These are not precise symbols of anything. They just are numbers that get fed into weights and biases. Okay, so in summary, what's going to happen here is these deep neural nets have many different layers, each one composed of many different neurons. but each neuron just operates simply. It's just got weights on each of its inputs, it's got a bias, and it's got a simple activation function. These, there's so many weights and biases that we're going to train these neural nets automatically. The most common algorithm for doing this is called backpropagation. I'm just giving you that name in case you want to look into it further. Each individual neuron is something that we can't understand directly other than just the input neurons and the output neuron. All the hidden layers in between, in some sense, mean something, but not in any way we can understand. Now, there are various topics that are going to be suggested for future research here. And one of the things that people are very interested in doing is figuring out how to explain what's going on in a neural net. Are there ways that you can take a neural net that works and transform it into one that still works, but has understandable parts so that we can understand what features went into deciding what should the price of this house be, or why did we classify your email as spam, or how did we decide that this person was likely to commit another crime in the future while this person was not. There's also various research on better learning algorithms than backpropagation. There's a lot of that going on right now. And there's also things that I haven't really mentioned at all about the architectures of the neural nets. I've so far talked as though every single neuron in the initial layer is connected to every single neuron in the first hidden layer by its own edge. And then each one of those in the first hidden layer is connected to each one in the second by its own uh, connection with its own weight, and so on. But it turns out for classifying images, you often want a lot of those weights to be matching each other. This is what they call a convolutional neural network. And in text, they do something else, which is called a transformer. And I'm not going to give you any of the details of that, but this is the sort of thing that people are doing in contemporary work on neural nets. They're coming up with different architectures, different ways of learning how to set the weights and biases automatically, and then trying to figure out what those neurons mean.